Thank you, guys. So this talk is going to be quite different from the last one. So as in we are going from extremely high level kind of to extremely low level. I'll start presenting ourselves. Myself, I'm an embedded systems engineer. I have 2 blogs, some stuff. And next to me is Roman. I'll let you present yourself.
Hi, guys. My name is Roman. I'm working in security, so I'm mostly doing attacks, side channel and fault attacks. That's what I do. And Matthew, he is an electronic designer, so he designs electronics. Actually, he works to design quantum computers. So if you want to ask him about this, you can do. And this talk appeared to be with a funny story. At a certain moment of time, we were in the same room. I was doing...
It's not what you think.
I was trying to repeat an attack on Jade crypto wallet, so I have a side channel attack to decrypt the flash content. He saw my setup and basically he was like, no, this is all wrong what you're doing. So it's an interesting view of electronic designer, like a view of person who understands electronics, how side channel attacks shall be done. So we're trying to combine, let's say, 2 approaches, attacks and knowledge of electronics, to present you today's talk. And we are going to speak about several things. So we are going to show you different side channel setups and problems which can appear by different connections and different, let's say, physical things. We will study wires, decoupling capacitances, probe, noise, power supply. Sometimes it's going to be tricky to understand, sometimes less. We are looking to find an ideal setup. We found it, and we, at the end of the talk, propose 2 very low-cost solutions to do side channel attacks, and these solutions can be used to attack any ESP32 on the market with, let's say, several minutes or hours. So that's why we're going to talk about ESP32. ESP32 has a cryptographic engine, hardware cryptographic engine inside, and we're going to attack it. So that's what we're going to do. And for each, let's say, setup, for each measurement, we will acquire side channel traces, 300,000 traces. Usually it's done within like less than 2 hours, 1 hour, 45 minutes each acquisition. We give some properties about the measurements, if you want to see them. And what we are going to analyze, we will show you raw traces, how they look like, how they change according to the measurement setup. We will speak about some frequency domain parameters, so we will show you Fourier transforms. And we will show you correlation, how measurement setup will affect correlation and how fast the key can be recovered.
Okay, so side channel attack measurements 101. So these are the different blocks that you will find on your test setup. I made the blocks as generic as possible because we are going to dig into one of them. In short, you have a power supply providing power to your device under test. So when I said DUT in this presentation, I mean a device under test. That DUT is a microcontroller, anything really, or secure element. It has some decoupling capacitors or not. We'll get back to that later. And you are going to use something, maybe current probes, differential probes. We'll go into the different hardware later. Connected to an oscilloscope. Usually it's a fancy oscilloscope, something that can do that has a bandwidth of 1 gigahertz. And then that oscilloscope is connected to your computer. Your computer is constantly triggering your device on the test to do something, and then fetching data from your oscilloscope that you're going to analyze later with your favorite high-level programming language. In Roman's case, it was Python. So we'll start from the very basic stuff, wires. Show of hands here. Do wires actually matter on a test setup? Do you think yes, no, yes? We have a couple of yes. That's good. So, okay. To illustrate that point, I made a simple experiment. So here you see 4 different test setups. On the left, 4 times, we have 4 signal generators. A signal generator is just a device that is generating a tone, a sine wave. In that case, that sine wave is going to be between 1 megahertz to 500 megahertz. On the right side, 4 times, you have a spectrum analyzer. A spectrum analyzer is looking at the frequency contents of its input. So if you're feeding 10 megahertz to the spectrum analyzer, it's going to see a big peak at 10 megahertz. As simple as that. 4 different wiring configurations. Number 1, this is a coaxial cable. I'm sure you're familiar with it. And then for the test setups 2, 3, and 4, same length of wires, just arranged differently. Who thinks here that makes a difference? That's good. Here, so I'm going to introduce that kind of graphs because we are going to reuse it quite a lot in the following slides. In the x-axis, you have the frequency. So as I said before, from 1 megahertz to 500 megahertz. In the y-axis, you have the attenuation. So that means that the higher the curves, the less attenuation you have, or the less signal degradation you have for a given frequency. Bottom line, and this will remain true for the remaining of the slides, the higher it is, the better it is, because you're losing less information. So going back to the previous wiring configurations, you see that the tighter the wires are together, the less you're losing information. So to give you an order of magnitude, with the bad wiring configuration, with the big loop, you actually have a degrees of 10 dB. 10 dB, this is 10 times in linear scale. Let's not care about the units, not important for the points I will bring later. So you see here that the bigger the loop, the more attenuation you have at high frequencies. It will become important later. Why? As some guy who is way smarter than me, Mr. Faraday, basically that says, okay, for any kind of wires of loop area, you're going to have a given inductance. The bigger the loop, the bigger the inductance. Why does inductance matter? In short, I'm a very low level guy. For those who don't work in electronics, I'm going to reuse that again a lot later. Imagine inductances as things that do not want to let the current pass. So the bigger the inductance, the more it will fight to let the high frequencies go through. Okay, that's enough theory. Can we actually prove this on an actual platform? On the bottom left, I'll stay close to the mic. On the bottom left, you see our device on the test that is connected to our measurement platforms that I will present later. So we have 2 test cases here. Feel free to interrupt me if I miss stuff, by the way. Either the device on this test is connected directly to our platform. So here you see direct solders from one to the other. Or 2 centimeters wires. Like 2 centimeters is not much, right? Supposedly. Time domain traces. So here you have supposedly the ESP32 doing some encryption thingy. You have the time domain traces of that current consumption during the AES encryption. You see here that in the case of no wires, you have a lot more spiky things. Spiky things means high frequencies. So that kind of illustrates the point, so actually does illustrate the point, that the longer the wires, may even be 2 centimeters, the more inductance you get, the less high frequencies you're gonna fetch. Next slide is actually time. So remember the graph I showed before. X-axis here you have frequency from DC to 1 gigahertz, and Y is intensity. Let's not bother about the units. So here what you clearly see is that in the case of no wires, which is blue, I apologize for the lack of legend, the blue curve is higher than the orange curve. That means that when you don't have any wires, when you're actually extracting your signal, you're going to get more high frequency, so more information. In the case of an attack, and I will let Roman actually present that one because I don't fully get it.
Sure, just to give more words about the traces, if you can give me a pointer. This is the entire trace of AES, including plain text and ciphertext transfers. So what you see here, it's a trigger beginning and the end of the trigger. First part, it's a plain text transfer. This is a ciphertext transfer, and AES is somewhere inside, in the middle. We don't see it from the trace. It's not possible to see. We just know that it happens there. So what we are doing, we are, let's say, taking some middle part of the traces, and we do side channel attack. So we apply Pearson correlation. We are attacking every single byte of the key separately. So it's a standard harming weight attack. And this shows the result when we apply different number of traces. So on the x-axis, you see how many traces we use to attack the setup. On the y-axis, you see the correlation. Gray traces indicate key guesses that are wrong. So there are 255 key guesses which are wrong. And the blue graph, blue trace, it's a correct key value. So basically what it means that when we don't have any wires, our correct key pops up at 75,000. It's 50,000. Okay, at 50,000 traces. And it keeps high all the time. So we could recover key fast. When we use 2 centimeter wires, our key pops up, let's say, later, significantly later. The distance you see is significantly smaller, so it's more difficult to understand which key is correct. We're still able to get it because it's the highest one, but the number of traces we need to get is also higher. So basically it implies that side channel attack with no wires, significantly faster, successful, and more, let's say, reasonable in comparison with 2 centimeter wires.
Conclusion, side channel attacks 101, do not use wires because it's going to take way longer for you to perform any kind of attack. So it's good in theory. In practice, you'll see that we actually have ways. Okay, going back to the initial attack setup that you have, power supplies, wires and everything, something that I always see around, and actually I was still a bit skeptical at first, but anyway, was, okay, whenever you want to attack one device, you remove all the decoupling capacitors. This is something that you see everywhere. I wanted to actually, is that true? So here's some run exercise for you, like, why do we need to remove the decoupling capacitors when all of your energy is coming from the battery, right? There is no secret energy source anywhere. All the energy is coming from the battery. So in theory, if you sense at the battery, you should see the current consumption. Actually, I'm trying giving hints here. Wires are inductances. Inductances are fighting high frequency currents. So in short, in a wiring setup, when you have the battery, you have the decoupling capacitors. Whenever the device on the test wants to take that high frequency currents, so what I mean by high frequency currents is that, for example, like it needs to toggle something. So when it toggles something, it needs to draw lots of current, lots is relative, lots of current at the given moment. Rather than fetching the energy all the way to the battery, it's going to fetch the energy at the decoupling capacitor. So actually what that actually means is that all the high frequency currents will be fetched from the decoupling capacitors, and the lower frequency currents will be fetched from the battery. It also explains the guidelines why whenever you do some layout, you always put your decoupling capacitors next to the microcontroller. So fine. Let's remove the decoupling capacitors, but unfortunately, the wires do not go away. So, what does that mean? That for the low frequency currents, whenever just standard current consumption, it's not going to make much of a difference at your microcontroller power supply pins, for example. However, remember that high frequency spike I mentioned before. In some cases, if you have wires that are too long, so long wires, long inductance will fight against current. When you have long wires, it is possible at your microcontroller pin that the voltage dip that I tried to illustrate here will be so low that your microcontroller will reboot. That happens. Concretely, on the device on the test, in the ESP32, all the red thingy are actually decoupling capacitors. So I hope you're good at desoldering. Oops, I think I skipped one. Okay, so same as before, different time domain traces, no capacitance, 0.0 microfarads. There will always be some small capacitance on the PCB, but let's forget that. 0.1 microfarad, 0.2 microfarad, same. You see here that less capacitance, more high frequencies, more spiky things. And if we look at it in the frequency domain, same as before, the blue curve higher than the rest here. So that means that you're going to get more information. So it's also valid across the spectrum. This is from DC to 1 gigahertz. So capacitance are not helping. In the case of the actual attack,
well, in the case of actual attack, we basically cannot make any attack with capacitance, because if we don't remove capacitances, our key doesn't pop up. But I put another slide, if you allow me, the key. This is a correlation not for the key, but for the ciphertext. So after the encryption is finished, we need to transfer the ciphertext outside, and I'm looking at the correlation of ciphertext. And in fact, for ciphertext, even with capacitances, we still see correlation. So when our capacitance is 0.2 microfarad, we see kind of like flat sinusoidal signal. If it's 0.1, we start to see appearing of high frequencies. But when we don't have any capacitances, our frequency, let's say, content is very high. So it implies that our measurements, first of all, they are correct. We're still able to see correlation of, let's say, slow processes like plain text transfers. But unfortunately, as we see in the attack traces, capacitances don't allow us to get the correct key with 300,000 traces. Possibly, if we do millions of traces, it will be possible, but that's not the goal. So we need to optimize our setup. That's why we need to remove capacitances.
Actually, if I may ask you a question on it, but so if I remember well, so this is the correlation for given ciphertext byte, and basically you have 255 traces that are more or less the same, but you can't make a difference. Is that correct?
No, this is just a byte of the ciphertext. You have 16 bytes of ciphertext, and you're supposed to have 16 correlation curves, but here I show only 4. It's only 4 bytes which I show.
Okay. So, conclusion. Remove all the capacitors. The old adage and general wisdom is actually true. That's good, I guess. Okay, so far we have done wires, we have done decoupling capacitors. Let's talk about the something here. So that something is supposed to allow you to measure currents. So to measure currents, many different stuff. So you have differential probes, you have current probes. I'm going to introduce them later. You have shunt resistors, just a resistor that converts current into voltage, resistor. Listen, I'll explain it later. And all of these measurement methods have a common selection criteria, which is the bandwidth. So bandwidth from the traces that you've seen before, from the graphs you've seen before, should have an idea of what that represents. So when you're trying to attack the ESP32, that ESP32 has 160 megahertz clock frequency. Can you have a guess of which frequencies you should be looking for when looking at the current consumption? If you are thinking 160 megahertz, you're wrong. So here is some more complicated traces.
Yeah, we're switching actually because we always have conversations with Matthew. So that's also we do during the presentation. We switch and he asks me questions and I ask him. So this is a bit more complicated to understand. But what we did as a test, we took our traces and then we filtered out from 0 frequency to a certain frequency. Let's say this is to 1000 megahertz filtering. This is from DC to 100. This is DC to 50 megahertz and DC to 25 megahertz. And we still were looking in the correlation, how many curves we need. Just be aware that we are using 100,000 traces here, not 300 as before. That's why this plot is a bit more, let's say, precise and you don't see nice difference. But it appears that when we filter out from the DC to 50 megahertz, we have the fastest and the best, let's say, distinguisher for correlation. If we filter it out more, then our correlation and distance between the correct and wrong key drops. Also, if we filter out, let's say, less, then our key also pops up later. And then this graph appeared. It's even for me difficult to explain and understand. So we are selecting high frequency. So we're doing a low pass filter from a DC to a certain frequency. So on x-axis, you see a frequency to which we are filtering from DC to this frequency. And then on y-axis, you see the maximum Pearson correlation coefficient for 1 key byte recovery. So these traces, it's 255 key guesses which are wrong, and the pink trace, because I like pink, it's a correct key guess. And we figured out that, in fact, when you filter out from 0 to 95 megahertz, then your correlation is the best. So you have the best distance, you have the highest correlation ever, but then for some reason, if you filter out not from 95 but to 100, so you add MHz content in your traces, your correlation significantly drops. Also, this particular graph shows that our CPU is running at 160 MHz, so somewhere here approximately. But we don't need 160 MHz content in our traces to attack AES. We need up to 100. So it implies that we need, let's say, low-level equipment in order to do the attack, basically.
If any of you guys know why we're interested, because we have no idea why. So just saying. Okay, so I was talking about stuff to measure current across a wire, or in that case, no wires. So going to introduce different tools, and keep in mind that in the case of the ESP32, we are looking at frequency contents up to 95 megahertz. Of course, if you have a different attack target, it's going to be different frequencies, and apparently your frequency you will be interested in will not be related to your main processor clock for some reason. So that's fine. Okay, so you have differential probes. In short, you put a resistor between the power supply and your device on the test. You measure the voltage across that resistance, and you connect it to your oscilloscope. They go up to 1.7 gigahertz second-hand on eBay for $500, but you do need the fancy scope that comes with it. So the fancy scope is going to cost you a pretty buck. You do have current probes. Actually, when I met Roman, he was using one. Current probes, they are clippy thingy that go around the wire. So you see I put the wire in red underlined. So you need to use a wire. Not ideal. And they fetch up to 100 megahertz, which in the case of the ESP32 is good. When I met him, he managed to do the attack without issue. It took quite a long while, but it worked. $275 second-hand on eBay, and any generic scope will do the trick. You do have listens. So if you were here last year, one was presented. What does a listen do? Basically, it isolates your power supply to your device on the test. So that means concretely, so you have your power supply, listen here, and then you have ground VCC going to your device on the test, and any current noise, so the current signal that you're interested in, will not go back to the power supply, but it will go to our amplification chain. Amplification chain is just a bunch of amplifiers, and then to your oscilloscope. This can go up to 430 megahertz, $250 when the one that was presented last year. So quite nice. The simplest setup of them all is a shunt resistor. So in short, you have your power supply, resistor, you AC couple. So AC coupling, in short, you're just looking at sines. You're not looking at the DC signal. You're just looking at frequencies from, let's say, 10 kilohertz and up. So you have your resistor, decoupling capacitor, you have an amplification or not, and an oscilloscope. The problem with that, so this is a bit tricky to get the point across, is ground loops. Ground loops, I'm not sure if any of you guys have experienced it, is, in the case of audio equipment, let's say you have your audio source on one AC socket, another audio source on another AC socket, and somehow you have that hum or that stuff. This is because current gets introduced through the ground, through your apartment house ground, so the earth, like you have currents going there, and basically it's impossible to make any kind of measurement. So if any of you guys try to use a shunt resistor and you found that it was not working, it's usually because of that. Your oscilloscope has an earth. Your computer is connected to the earth. The power supply, depending on if you connected that green wire or not, has an earth. So it's easy to get it wrong. Very easy to get it wrong. We came here to present devices. This is one of the devices that we are releasing. In short, it's a board that provides the power supply to your device on the test, has a shunt resistor, but the amplification on the board itself. So therefore, it isolates itself from everything. You connect an oscilloscope, so up to 1 gigahertz for $125, and it is a low side measurements. What are low side and high side measurements? So in short, low side and high side measurements is just a fancy word to say where I'm putting that shunt resistance. If I'm putting it between the power supply ground and my device on the test, it is a low side measurements because ground is low. And if I'm putting that shunt resistor on the VCC or the 5 volts, 3 volt, 1.2, whatever, this is a high side measurement. So that board that you're seeing here, this is a low side measurement device. Because I was on fire and I wanted to play, I made another board, which is a funky little device that allows low side and high side measurements. In short, you take that board, you see the two holes here. You connect it inline with the device you want to attack, because I realized that in some cases, when you have some fancy system on modules, it is not easy to just like remove all the components and you just have a trace you want to cut and measure there. So this device was designed for that purpose. So here I'm going to increase the level of required knowledge to understand that. So in short, I'm using a balloon, which another way to say I'm using a transformer. So in short, the DC current, so the static current consumption, is going through a resistor, but the high frequencies that we're interested in, using the decoupling capacitor here, is going through a transformer. So the left side of the transformer is isolated from the high side, so whatever current is going there is mirrored, kind of, here, and then it is amplified going to your oscilloscope. So this is one of the devices that we're presenting. I'll show the schematics later. So all of these tools presentation, we were talking about bandwidth originally. So if we just take into account the frequency criteria that we're interested in, again, in the case of the ESP32, it was 95 megahertz. Any of them will do. Like, see, if you just look at the frequency contents, the tools bandwidth, anyone can do 95 megahertz. So if you just took the bandwidth at the selection criteria for all the measurement method, take any of them, take the cheapest. However, is there something that should be taken care of, something that we should be aware of in measurement method, setups? The noise, or as my friends would say, myself after 2 beers. So the noise. Where is the noise coming from? The noise is coming from everywhere. So you have your power supply is generating noise, your probe is generating noise, your amplification chain is generating noise, your oscilloscope at the input is generating noise. Everything is generating noise, and fairly annoying. I will start sources of noise. I will start with the noise from the environment, yes, truly. So to illustrate that point, we just took a microcontroller, we had it run a while one loop, and in another case, we let it hibernate. So here you're looking at the current consumption of when the device is doing nothing, or when the device is just doing a while one. And you see that you have many spikes that are the same for both traces. So that means basically that your measurement method, and this is across all measurement methods you can think of, your measurement is taking noise from your environment. Unfortunately. Noise sources, oscilloscope. This is my favorite oscilloscope at the time. Whenever I have enough money, I'll buy it. Very low input noise. When I met Roman, actually, I think he was affected by this kind of noise. So there is one trick when you have an oscilloscope that has too much input noise, is that you just enable the averaging. You press the averaging button, you say, I want 100 traces that are averaged. When I got my 100 traces, I'm fetching them on my computer. You have a signal-to-noise ratio improvement. Anyway, you're getting more signal, but unfortunately, you're trading off time here. So like your attack is going to take way longer. Another attack, so another fun stuff is the importance of power supply. Oh, maybe you can comment on this one.
Right. Matthew said a lot of different things, and we will sum them up slowly. One of them is about power supplies. So we can use a lab power supply, like a desktop lab power supply, use cables to connect to the target. And this is a case of the middle trace. We can actually use a battery power supply, so just a stable battery. A battery is sometimes also possible, but we use battery through LDO, and this is a correlation traces for battery plus LDO. Or we can use a power supply plus LDO. So you see that if we use a raw power supply, our correlation basically doesn't work with 300 traces. We need significantly more number of them. But if we just add LDO, or if we use a raw battery, our correlation pops up quite fast. It means that power supply has a lot of noise itself. We need to filter this noise out.
Lots of noise. So, continuing on the sources of noises. You have the current probe. So here I'll gloss over the details because come talk to us later if you're interested. Bottom line is that your current probe has noise itself. This is a very fancy current probe, 75 microamps RMS max. So that effectively means that if you're trying to measure any current that is lower than 75 microamps, you're not going to be able to easily extract your signal. It's still possible using some averaging, but when your current probe has noise that is in the order of magnitude of the current you're trying to measure, then you're going to have a bad time. Differential probes, looking online and everything. So you typically have 28 microamps RMS noise. And again, you still need to buy the compatible scope. Before that was $6K. This is second-hand, $500. Still, you need the fancy oscilloscope that comes with it. Amplification chain. If you remember the diagram I keep showing up, you have something that is measuring the current, and maybe you need to amplify whatever that something is outputting. So you have amplifiers. Just to make stuff more fun, they don't mention microamps RMS noise. They just mention a noise figure. So basically, they say how much noise is added to an ideal amplifier. Bottom line, very good. Amplifiers is actually what is being used in your phone. They have very low noise, and it's in all your advantage to have low noise on this one. Okay, so I mentioned many sources of noise here, so I'm going to summarize all of them and explain how to decrease, how to optimize for noise. So probe, every probe has a noise, don't use a probe. Environment, unless you live in a Faraday cage, not much you can do about that. Optimizing for noise for power supplies, you use a power supply or you filter your lab power supply output using some LDO, so low dropout regulator. Amplification chain, but basically, as I mentioned before, amplifiers, they have very low noise figure, like they don't add much noise, so it's free. Measurement instruments. So here's the interesting trick. So I mentioned that the oscilloscope has an input noise that may perturbate your measurements. The trick here is basically you amplify. So if I point here, so the trick that you can use is amplify enough that basically the input noise of your oscilloscope does not matter anymore because you're flooding your oscilloscope with noise and therefore it doesn't care about its input noise. And so actually what I'm suggesting here is exactly what your phone is doing. Your phone just has an antenna, then it has a simple antenna, doesn't have sensor, and has an amplifier, and that amplifier output is digitized by any analog to digital converter or different techniques. Okay, so I told you about bandwidth, gains, input noise. I'm sure you're confused by now. Let's compare different measurement methods and mention the points I brought up before. So here we are comparing in the time domain the same AES traces, but measured with different measurement methods. And in each test setup, we should have taken many pictures, that was fun. And for each test case, we are optimizing for no wires, decoupling capacitance. So we are putting ourselves in the best test setup in order to compare, or as much as we can, compare the different tools to measure the current consumption. So design number 1, design number 2, listen, current probes, differential probes. You see that our two designs have more spiky things, more high frequencies. So that means good. Otherwise, we wouldn't be here today, I guess. If we look at the frequency domains, this is actually quite fun. So two takeaways from this graph. The red curve, this is the frequency contents when used with the current probe. Remember that 100 megahertz bandwidth that I mentioned? You can clearly see it here because from 100 megahertz you don't have anything. It's just going all the way down. For the current probe, you just get some frequency contents at less than 50 megahertz, something like that. Another takeaway that I find interesting is that the differential probe that I mentioned before, you see it's flat and then goes like that. So that means that here, really, you have so much noise coming from your differential probe that you are not going to be able to perform any kind of attack. Talking about attacks.
Yeah, if you lost us during the last 10 minutes while Matthew was talking, I believe it's difficult to recover your attention, but still. What it means for an attack? Very short. Current probe and listen with 300,000 traces can give us the correct key, more or less, at the end. Differential probe never was possible with 300 traces to get anything. But if we speak about design that Matthew presented, the first one, like big board, gives a very good correlation at the beginning, already with a small number of traces. And the second device, when you connect to the VDD, so the first one you connect to ground, the second you connect to VDD. VDD also works fine. It's a short story.
Short is good. So how did we do it? So I promised you we would present the platforms that we designed. So I'll start with approach number 2. Tiny PCB, again, that you put in line with wires here on your board. So this is the diagram I presented before. You have the DC current that is going to go there. So you have a potentiometer, because in some cases you might want to adjust the gain. So it's always tricky. So when you connect your wire, your test setup in the first place, it's always tricky to know if you're getting a good trace or not. So you may want to play with the gain. Filtering is a bit more tricky. You have inline filters, but I will not mention them. So basically we have a potentiometer that allows you to set your base shunt resistance, adjust the gain at the output. You have a balloon that allows you to isolate this side with this side. That means that basically you're not creating any ground loops. Lots of amplification, high amplitude signal, going to a second-hand oscilloscope. Here I was aiming for something that had 500 megahertz, 1 gigasample per second sampling rate. This is $600 on eBay. So I'm really trying to destroy hard the stereotype that you need fancy equipment to perform side channel attacks here. Again, okay, so you still need, so depending on your attack setup, in some cases you may still need some filtered power supply that we mentioned before, that you need to have a clean power supply. On AliExpress, you have this kind of boards that basically you put a 18650 cell, it has LDOs, and you just solder wires, and this should be enough. Or in that case, try to not solder wires, connect everything together as close as possible. So this is $25. If you want, we have some with us. Like again, I'm really fighting hard to make side channel attacks accessible to everyone. Concretely, schematics for the electricians, electronics engineer out there. This is what it looks like. So I'm just using RF amplifiers that are typically used for, I think, walkie-talkies, I think. I just published on my website a technical write-up. So here you can see the frequency responses and a lot more mumbo-jumbo of electronics. Approach number 1, so this is the big boards that provide the power supply to your device on the test. So this is the key in-hand solution. DUT here, and you have 3 solders. 2 solders. 1 for ground and 1 for the power supply. You connect your oscilloscope here, and you have your signal. Again, just a shunt resistor with some amplification, provides power to the target, 3 different voltages. Will be released in a week or 2. I'm currently having it produced because we want to improve things. Ways to join us or to stay informed of when it is released. Schematics, not going for RF amplifiers, I'm going for op-amps because they're fun. So potentiometer, two stages of gain. We are about to release a version that has variable attenuation, because during our attacks, we've seen that many different platforms leak in very different ways. As in, you would have a platform that would leak very little, and you have another platform that would leak a lot. So therefore, you need to have variable gain. So next revision, again, because website will be released to make it accessible to everyone. Conclusion. Hopefully you're still with me. Best side channel are there. What should you do? Do not use wires, probes, power supplies. Use batteries, in that case, is what I meant. Remove decoupling capacitors. Use a cheap scope without cheap bolts, if you want to, of course. And if you have any question, we'll be more than happy to answer.
Thanks, guys. So we have some room for questions. Do we have questions in the audience? Yes, we do. All right.
Hi. You mentioned that removing decoupling capacitors improves the signal. So from my understanding, you're doing the voltage measuring. Does that also apply to EM side channel attacks?
This is difficult to answer, unfortunately. So when we do the electromagnetic measurements, we didn't conduct any research if removing decoupling capacitances improve electromagnetic measurements. So we didn't do it. I cannot comment about this a lot.
Actually can.
Mate, you can.
So, actually it will improve, and actually our next speaker will be able to explain that better than we are. In short, so it's all about the loop area. So here I'm showing a small loop. So remember this high frequency currents. In the case of decoupling capacitors, your loop area for this high frequency current is very small. So that means this loop is an antenna in some sense. So when you're removing the decoupling capacitance, you're forcing the high frequency currents to go through here. So you have a bigger loop antenna, therefore more emissions. So therefore, if you have your spectrometer with your antenna, you will fetch more EMI if you're removing the decoupling capacitors.
Thank you.
All right. Do you have any other questions? Anyone? 3, 2, no. All right. So let's give a round of applause to the guys.